Okay, in this video I'd like to address three of the problems from our practice test, 7, 9, and then 11. With 7 and 9, we're using acceleration and velocity functions in order to find a position function and use that position function. With number 11, we're being asked to find the area or approximate area under a curve using an appropriate Riemann sum. Now, if you're using the answer key at the end of the test, I believe the answer in number 11, well, number 11, 12, and 13 for that matter, I think they only report the result of the left-hand sums. And that's because I modified the instructions and did not modify the answer key. So that was my mistake there. So anyway, I'll walk through that process and hopefully give you a better idea of how I would approach a problem like this. Okay, with number 7, again, we're given a velocity function, so we know how fast an object is moving at any given time. This t value, we can substitute a number in and find out how fast the object is moving. And what we need to remember is the progression of derivatives with position, velocity, and time. So way back in Unit 1, we said the position of any object has a derivative. If we were to find the rate of change of position, that would be velocity. And then if we were to take the derivative of velocity, or the rate of change of velocity, that would measure acceleration. So in this progression, if we had a position function and we went down this list, we would find a derivative of position to locate the velocity function. The derivative of velocity is acceleration. But the opposite is true when we're working backwards. If we have the acceleration function, its antiderivative is velocity, and if we have the velocity function, its antiderivative is position. So what I sometimes like to do is, beneath the velocity function, I'll write velocity with a capital V, because remember, capital letters at this point in the class tend to represent antiderivatives. The capital V of t is also equal to a of t, because the antiderivative of velocity is acceleration, and that would be equal to the antiderivative of this particular function. Whoops, I said that incorrectly. Antiderivative of velocity is position. Sorry about that. And that's what we're after here. So as far as finding the antiderivative goes, I'm going to report my coefficient, and then I'll increase the degree or the exponent. And I do this for each of the terms. And after I do this, then I'll simplify. Now, I don't know what the constant is, because there will be, or there is almost always, some constant value in the position function whose derivative is 0, and that's why it disappears in the velocity function. So we don't know what that is, but we're going to use this initial value to determine that. So I'll drop the antiderivative notation here. That was just to remind myself of how these two equations are related. And then I'll clean things up just a little bit. This negative 3 and this positive 3 will reduce to 1. So we're now dealing with negative t cubed. 46 divided by 2 is 23 t squared minus 120 t plus c. Now here again, we need to know what this c value is. It could be any numerical constant. And the way we do that is we incorporate this supplied piece of information. What we know is that s evaluated at 0 will equal 0. And when we say that s is being evaluated at 0, what that implies is that the letter t has been changed to the number 0. And when t is equal to 0, then the entire result is equal to 0. That's exactly what this little phrase is saying here. And so when 0 is equal to all of this, we know that 0 is equal to, well, everything here is going to turn to 0. So 0 is equal to 0 plus c, therefore c by itself is equal to 0. And then finally, we can state that the complete and original position function is the opposite of t cubed plus 23t squared minus 120t plus 0. And we don't need to show that plus 0. Now, if the given value was slightly different, which is entirely possible, There are scenarios where we might say s evaluated at 2 is equal to 0. Well, all that does is it changes this line right here. So I've just made a copy of that and set it off to the side here. So if we're saying that s of 2 is equal to 0, then what we're saying is that by substituting the number 2 into the equation, then we'll end up with a result that's equal to 0. So if we had negative 2 cubed plus 23 times 2 minus 120 times 2 plus c, that would all equal 0. And off camera, I calculated that to be 78. So if we had negative 2 cubed plus 23 times 2 minus 120 times 2, that equals 78. So this expression is 78, and if 0 is still equal to 78 plus c, then this c value for this particular example would be negative 78, and our position function in this particular example would have been negative t cubed plus 23t minus 120t minus 78. Now these two functions are very similar in that the components with the variables are exactly the same, only this guy here in green has a secondary constant. But if we were to find the derivative of each of these, both would be exactly the same. The derivatives of each end up equaling the original velocity function that we had. Both derivatives end up being negative 3t squared plus 46t minus 120. And that's important. And if we're thinking a little bit about what this problem is really trying to describe, remember, we've got this particle. All it can do is move back and forth on this coordinate line. It can only move left and right. And in this blue example here, we're saying at time 0, this particle is right here at position 0, and I'm going to call the center of this line position 0. So we don't know where it was at at any other points. Originally, we were told the only location that we knew of was that at time 0, its position was 0. But in this second example, we had said, well, at time 2, its position was 0. So it ended up being at this position here, at the center again, but that occurred at time 0. And interestingly, since we have a position function, we could find the position now at any given time. But let's consider what would have happened here if we had substituted s with 0, substituted t with 0. So at time 0, in this particular case, the position is negative 78. So we did not know where this was originally, and even if we were told that the position at time 2 was equal to 0, we now know, using this particular equation that we established, that at time 0, that particle's position would have been somewhere over here. And so here again, the nice thing about these types of problems is that measuring velocity is something that can be done when we're observing a particle in this space. And maybe recognizing the position of a particle in one spot might be doable in this particular space. But determining the other positions, where the article is at any other given time, that would require a little bit of investigation, and that's essentially what we've done here. We've investigated and analyzed the equation and established a new equation that tells us the position of that particle at any given time, not just at time 0 or time 2 in this case. So as far as the test goes, I'm really only asking you to do essentially this component. This secondary example over here was just something that I used to hopefully explain this situation a little bit better. Let's try to be a little bit more streamlined, and we'll complete problem number 9 exactly as it's written. Except I did modify this question, and I will have it modified for the test as well. If I give you the acceleration, I would like for you to be able to work backwards and also find the position at a given value for t. So not just velocity, but also position. Okay, so again, the antiderivative of acceleration is velocity, and the antiderivative of negative 6t is going to be negative 6t squared over 2 plus 2 times t plus c. This would simplify, of course, to negative 3t squared plus 2t plus c. And we need to identify the c value before we find the antiderivative in the next step. And fortunately, we were given this piece of information. When v of 0 is evaluated, it ends up being 56. And so that means that 56 is equal to negative 3 times 0 squared plus 2 times 0 plus c. So 56 is equal to 0 plus c because these terms turn to 0 when evaluated at 0. And we now can easily recognize that c is equal to 56 in our velocity function. So when written in totality, the velocity of this particular particle is negative 3t squared plus 2t plus 56. Now our goal is to find position. If we were completing this problem to find the velocity, well, we've got the velocity function now, and we can substitute t value of 7 into the velocity function and be done. But I am asking you to go a step further, so we will do that. Now, the antiderivative of velocity is position, which is what we're after here. And so the antiderivative of this one, of course, would be negative 3t cubed over 3 plus 2 times t squared over 2 plus 56t plus c. And when simplified, this position function might look like negative t cubed plus t squared plus 56t plus c. And here again, we were given some preliminary information. The initial position function said that s evaluated at 0 was equal to 0. So that means that when 0 cubed plus 0 squared plus 56 times 0 plus c is evaluated, we end up with 0 as the result. So 0, of course, is our c value for the position function. And so that tells me that our position function, s of t, is equal to the opposite of t cubed plus t squared plus 56t plus 0. And now finally, since we're being asked to find the position of this particle at time 7, well, we can substitute 7 in place for t. So we've got negative 7 cubed plus 7 squared plus 56 times 7. And off camera, I calculated that to be 98. So at the very beginning of this problem, we only knew how fast the particle was accelerating based on this function. We could determine its acceleration based on any time value, but that's the only information we had, along with the initial position and initial velocity. And as it turns out, we were able to compute a position function, so we could locate the position of this particle or where it exists at any given time. We were also able to compute the velocity function, so we would know how fast the object is moving at any given time. And then ultimately we were able to answer the question at hand, the position of the particle at time 7. And now we'll move on to number 11. For these problems on the test, you can choose whether to complete left, right, midpoint, or trapezoid sums. We haven't practiced much with trapezoids, so I wouldn't be surprised if most of you skip that. Midpoint, of course, some of you can recognize that process and will use it. But with the left and right hand sums, as we talked about in class, it's best to utilize both of these and find the average of them in order to get a good approximation. So I'm going to walk through that process here with number 11. Now if you choose midpoint, I think that that technique is perfectly fine. That by itself will give you a pretty good approximation. But typically left by itself or right by itself doesn't give us a great approximation. So our job is to evaluate the area under this curve between 0 and 4. So right off the bat, I'm going to mark my interval between 0 and 4. And we're being told to use 4 sub-intervals. So the sub-intervals are here, here, and here. So now we've got 1, 2, 3, 4 sub-intervals, 4 rectangles that can be built based on the height of this graph. Now, with left-hand sums, what I need to do is find the height of the graph in these 4 positions here. I don't know what the height is, so I'm going to have to evaluate that in the function. But on the left-hand side, each rectangle is built, with a left-hand sum, each rectangle is built with the left-hand data point. On a right-hand sum, what happens is we ignore this value, and in its place, we use this value. And that's going to create 4 rectangles whose height is determined based on the right-hand side of the subintervals. And so that's why I say computing the left and right-hand sums is pretty easy. Once you have one, a simple modification will allow you to find the other. Because again, once you have your left-hand sum, you simply eliminate that first data point and then calculate the last data point, but you'll reuse all of those that are in the middle. So here we go. I need to evaluate this function y at 0. I need to evaluate it at 1, at 2, at 3, and at 4. We need all 5 of those to do both the left and the right-hand sums. And this is a bit of unconventional notation, but if you were to write this, I know exactly what you're trying to do. You're evaluating the function y at 0, and so on. So if we evaluate this function at 0, that's pretty easy. 0 plus 9 is 9. So the height of the graph is 9 units at 0. When we evaluate at 1, well, that gives me 1 squared negative. So that's negative 1 plus 2 plus 9. Well, that comes out to be 10. Then at 2, we've got 2 squared, which is 4. With a negative sign, so negative 4 plus 9, that equals 9. When evaluated at 3, that's negative 9 plus 6 plus 9. And when evaluated at 4, that gives me negative 16 plus 8 plus 9, which is 1. So if we needed to plot this graph, if it wasn't given to us, we can fairly easily determine the data points that go into the graph. And so we essentially have this parabola in place here. Now, I'm not going to leave this parabola on the screen, but that's the shape of this particular graph. I'm not going to leave it on there because we're using a Riemann sum to approximate the areas, and what we're really interested in are the areas of these particular rectangles. And so what I'm drawing in right now are the left-hand rectangles. So I've got 4 of them, and they essentially cover the space of the parabola, but each one of these rectangles were built based on the heights established on the left-hand side of the subintervals. So when it comes to our left-hand sum, the sum of the rectangles from the left-hand sides, well, this particular rectangle here, sorry, I went too far. This first rectangle has a width of 1 and a height of 9. The next rectangle also has a width of 1, but a height of 10, and then a width of 1, but a height of 9, and a width of 1 and a height of 6. And so I would have had 1 times 9 plus 1 times 10 plus 1 times 9 and so on. All of those rectangles share this 1 in common, so the practice that we've been using in class is to use the width of our rectangles out here as a leading coefficient, or I should say a value that would distribute in, a common factor, and then list the heights of the rectangles here. That would be particularly helpful if say we were looking at the interval from negative 8 to 0 on 4 subintervals. Well, now the width of each rectangle in a graph like this would be 2 units wide. And if we've got 2 units in width, times the height, well, we would use 2 as our value outside of our grouping symbol. So our left-hand sum we can pretty easily calculate since the sum of this is multiplied by 1. And so we've got 19 and 9 is 28, plus 6 is 34. So our left-hand sum is 34. Our right-hand sum is very similar. We use this, and this height again, because now, let me just jot this down. 10 plus 9 plus 6, because now when we're talking about the heights of these rectangles, we're building them off of the right-hand data point. So this first subinterval has the height established from this data point, from the right to the left, and then this data point. So there's our height of 10, and then our height of 9, and now our height of 6. And then the final right-hand rectangle is built here with a height of 1. And so with our right-hand sums, we're still trying to approximate the area underneath this parabola, but the right-hand sum rectangles have these heights here. So 10 and 9 is 19, and 6 is 25, plus 1 is 26. So the right-hand sum is 26. The average, of course, of 34 and 26 would be 60 divided by 2, which is 30. So our approximation using left and right-hand sums averaged together would be 30 square units. And to satisfy my curiosity, let's just point this out here. We've learned enough about definite integrals that if I wanted to find the exact area under this curve between the curve and the x-axis, what I would need to do is integrate from 0 to 4 on this function with respect to x. And off screen, I used a calculator to compute this, and that comes out to be 92/3, which is approximately 30.6 repeating. And so if that's our exact answer, I would say that this was a pretty good approximation. 34 was okay, 26 was okay, but you can see how far off from the actual answer they actually were. But when computing the average of them, well, the average ended up being very, very close. So I hope this video helps explain the process or the procedure that I would use for these particular examples. If you've got further questions, or if any of you would like to see how I would approach the midpoint technique, that way you can decide whether it would be more efficient for you on the test, I'd be happy to do that upon your request. Thanks for watching.